My name is Bruno Villaseñor. I'm a graduate student at UCSC working with Brand Robertson, Pierre Amadao, and Evan Schneider. And thank you for joining me. I will be talking about my recent work inferring the thermal history of the IGM by comparing two large-scale Lyman-alpha Forest power spectrum. Just as an introduction, the Lyman-alpha Forest is a collection of absorption features that we observe in the spectra of distant quasars and galaxies. These features occur because as the light emitted by the quasar travels through the intergalactic medium, it encounters clouds of neutral hydrogen, and the photons with the frequencies that correspond to the Lyman-alpha transition of hydrogen will get scattered by the presence of the neutral hydrogen atoms. The Lyman-alpha Forest is a powerful tool for cosmology. To start, it probes the density fluctuations in the IGM. Also, the absorption features encode information of the temperature of the gas, allowing us to estimate the thermal state of the gas in the IGM. Additionally, since the forest is only sensible to the neutral hydrogen, we can estimate the amplitude and time dependence of the UV background from studying the forest. Also, it allows us to probe the density fluctuations at very small scales, making it possible to constrain models for warm dark matter and neutrinos, which would suppress small-scale structure. Finally, from the correlations of the Lyman-alpha observers, we can reconstruct the signature of the baryonic acoustic oscillations, and from that measure the expansion history of the universe and the growth of large-scale structures. One way to study the forest is to measure the average statistics from many samples of Lyman-alpha spectra. This is made possible by surveys like BOSS, which has collected tens of thousands of spectra from quasars at different redshifts. Here on the left, I show one of such spectra observed by BOSS, and on the right, you see the average power spectrum from a sample of more than 40,000 quasar spectrum from redshift 4.6 to redshift 2.2. The physical scales probed by this measurement are about 90 comoving megaparsec on the left to about 5 comoving megaparsec on the right. And this is great because on scales of a few megaparsecs, the power spectrum of the forest is an excellent probe for the thermal properties of the gas in the IGM. And on smaller scales, the power spectrum also allows us to set constraints on relevant physics like the properties of neutrinos and the nature of dark matter. And this is a great time to study the Lyman-alpha Forest because DESI is on the horizon. And as you might know, DESI will have an extremely dense sampling of quasars over a huge area in the sky of more than 10,000 square degrees, providing us with hundreds of thousands of quasar spectra. This will allow us to have an extremely detailed view of not only the astrophysics of the forest itself, but also of the cosmology that we can measure from the forest. And with the advent of these great experiments like DESI, we also need to advance the methodology that we use to construct the theory as well. This means that we need to improve the cosmological simulations that we use to compare to the data and constrain our models. In particular, a few important points are that we need to solve large cosmological volumes to compare to the large scales probed by these large surveys. But on the other hand, we also need to resolve the small scales with high resolution to allow us to set constraints on our physical models. Additionally, we want to understand and reduce the systematics in the simulations to make sure that we are accurately solving the relevance physics of the models that we compare to the observational data. And finally, we need fast, efficient tools that allow us to run multiple simulations covering a wide range of parameter and physical models. With this last point in mind, the way we are going to accelerate our calculations is by making use of GPUs. And this brings me to Cholla. Cholla is a new code that was originally developed by Evan Schneider and Brand Robertson. Cholla is a state-of-the-art grid-based hydrodynamic solver that runs natively in multiple GPUs. And of course, for cosmological simulations, there are more physical processes involved. So for the first part of my PhD, I have been in charge of engineering those physics into Cholla. Here I show a timeline starting in 2016 when Cholla originally was the hydro solver. First, I added a Poisson solver for set gravity. Then I added a comoving coordinate system for the expansion of the universe. Then I implemented an M-body integrator for the dark matter particles. Also, I coupled Grackle into Cholla to do primordial chemistry and radiative cooling. And finally, I provide photoheating and photoionization rates to account for hydrogen and helium reionization. So now Cholla is a fast, robust code to perform cosmological simulations. Cholla runs in the largest computers of the world. In particular, we have been using Summit, and Summit at Oak Ridge National Lab is the #1 fastest supercomputer in the US. All the simulations that I'm showing you here, I run them on Summit. Okay, so how do one of these simulations look? On the left, you see the evolution of the gas density, and on the right is the temperature of the gas. And you can see how at early times in cosmic history, reionization hits the gas, and then as structure continues to develop, the gas heats up as it collapses into the large-scale structure. Okay, so in the animation we saw the effect of reionization heating the gas. And the way this is implemented is by constructing photoheating and photoionization rates by integrating the intensity of the radiation from the ionizing sources. This is shown in the first equation on top. The mean intensity J is connected to the emissivity of the galaxies and quasars, but it's also connected to the mean free path of the ionizing photons. This is basically how far the ionizing photons can travel. One of the standard models for the UV background is the one made by Hart and Maddow back in 2012, but this model has a problem, which is that they overestimated the mean free path of the ionizing photons for high redshifts, which leads to a reionization that happens very early in the simulations, around redshift 14. This issue was addressed in a recent model by Phuc et al. In 2019, where they changed the mean free path so that now it presents a sharp transition at redshift 6. You can see this in the top figure, where the white line is the mean free path for the Hart and Maddow model, and in yellow you see the sudden increase in the Phuc model, which causes reionization to happen more realistically around redshift 6. Okay, so the photoheating from the UV background is driving the heating of the IGM. Here now I show the density temperature distribution of the gas in one of these simulations, and as you can see, most of the volume of the box is occupied by low density, low temperature gas, which corresponds to the gas in the diffuse IGM. And furthermore, you can see that the diffuse gas follows a tight relation that corresponds to the power law shown in the right, where T0 is the temperature of the gas at mean density, and gamma, which is the index of the power law, corresponds to the inclination of the distribution. This relation is set by the balance between photoheating from the UV background and cooling from radiative processes, as well as cooling from the expansion of the universe. Unfortunately, we cannot measure the thermal structure of the gas directly from observations. So what we're going to do is to construct Lyman-alpha Forest from the simulations and compare their properties to the observations. Here I show how we trace multiple skewers crossing the simulation box, and along each skewer we compute the optical depth, which is proportional to the neutral hydrogen density multiplied by a Gaussian profile, and the width of the Gaussian is set by the thermal velocities of the gas. Then we compute the transmitted flux along the skewer from the optical depth, and the bottom panel of the image shows the flux along this particular skewer on the top. Okay, now we're going to compare the properties of the Lyman-alpha Forest from the simulations to the observations. In my paper from earlier this year, I compared the forest from simulations using the two models for the UV background that I mentioned before. Here shown in blue for the Hart and Maddow, and in green for the Phuc model. The data points correspond to the observation from BOSS that I showed in the introduction. And basically, what you see is that neither of these models matches the observations precisely. Instead, the data lies in between the models. To find the photoheating and photoionizations that match the observations, what we did is that we construct modified rates by applying two types of transformations to the rates from the Phuc model. The first transformation is that we are going to multiply the rates by a scaling factor beta. So here you see the rescaled photoheating and photoionization rates for hydrogen. Note that we are modifying both the heating and reionization rates equally. Okay, the second transformation will be a shift in the redshift dependent of the rates. Basically, we are shifting the time where reionization occurs. Here again, you see the effect of applying this shift that we named delta C, applied equally to both heating and ionization rates. We do the same for helium-2 rates, so we rescale and shift the photoheating and photoionization rates equally. This leaves us with 4 open parameters that control the reionization histories in our simulations. Now we run a grid of 400 Cholla simulations for different combinations of our 4 parameters. Each simulation is a 50 H inverse megaparsecs box on a 1024 cubed uniform grid. So these are relatively high resolution simulations for a simulation suite of this magnitude. And we believe that the scale of this simulation grid is unprecedented and only made possible by using a fast code like Cholla and access to a supercomputer like Summit. Okay, this image shows a slice of the temperature at redshift 3.6, and you can see the effects that the different values for the pair of helium parameters has on the temperature at this epoch. Basically, increasing the scaling parameter beta helium in the x-axis increases the temperature of the IGM by increasing the net helium-2 photoheating rate. And moving in the y-axis towards larger delta C values also increases the temperature because helium reionization happens earlier, closer to redshift 3.6, which is what is shown in this image. Now you see all the different thermal histories from our 400 simulations, and you can see how we can create a large variety of thermal histories from the different reionization histories. The different reionization histories also have an effect on the neutral hydrogen in the IGM, and as you can see here, these effects combined to the different thermal structures of the gas results in variations of the Lyman-alpha power spectrum on a wide range of scales. Something to note is that the amount of variation induced by each parameter is different and also redshift dependent. Okay, then the approach to find the best model that reproduces the observed power spectrum will be to use an MCMC to sample the parameter grid and find the distribution of parameters that maximizes the likelihood measured from the simulated and observed power spectra. Something important to note is that we are not feeding each redshift separately. Instead, we are feeding the entire self-consistent reionization histories to the entire BOSS dataset. This is because the properties of the IGM at one redshift are not independent from the state of the IGM at the different redshifts. Okay, so here I'm just showing 3 redshift snapshots, but we feed jointly to all the BOSS power spectra from redshift 2.2 to 4.6. Finally, to have a better constraint for the helium parameters, we also include the measurements of helium-2 effective optical depth from Warsack et al. Into our likelihood calculations. Since helium-2 only affects the Lyman-alpha Forest by its effect on the temperature, then by including the helium-2 optical depth, we are also informing the model about the amount of helium-2 present in the IGM. Okay, so we proceed to feed the reionization histories to Lyman-alpha power spectrum and helium-2 optical depth, and here are the results for the posterior distributions of our 4 parameters. What you see is that the 4 parameters are well constrained. On the right, I show the values of the parameters resulting from our analysis. These parameters tell you how to modify the Pooquine rates from the Pooquine model to fit the observed power spectrum. Okay, so now let's see how well this new model performs. Here I show our resulting Lyman-alpha power spectrum marginalized over our posterior distribution. And you see that the modified photoheating and photoionization rates produce large-scale Lyman-alpha power spectrum that is very close to the BOSS measurement. We also fit to helium-2 effective optical depth, and here we see that our model is also consistent with the measurement from Warsack et al. Okay, now you see a result for the thermal history marginalized over the posterior distribution, and I show that our inference for the thermal state of the IGM quantified by T0 and gamma is consistent with the inference presented last year by Gaikwad et al. It's important to note that these inferences are completely independent. Gaikwad uses other datasets, other simulation suite, and in general other methodology. Nevertheless, we infer similar thermal histories. This is remarkable and it's important. Okay, the last thing I'll be showing you is the marginalized photoheating rate for hydrogen compared to a variety of other inferences. You can see that in general, our result is consistent with most of the other inferences and consistent with hydrogen reionization happening around redshift 6. Now to finish, you will see an animation that I made from one of my high-resolution simulations showing the formation of large-scale structure on the gas density. Okay, we've reached the end of my presentation. These are the conclusions for my talk. I hope you enjoyed it, and if you have any questions or concerns, feel free to reach me at my email, which is in the first slide of this presentation. And yes, thank you.